Thank you for inviting me to India. It's an amazing place. I was here once before, but it was a long time ago. It's nice to be back. Right, so I want to talk about Euler characteristics of spaces of graphs. Right, with no grid lines. Okay, so what kind of spaces am I talking about exactly? The basic space, you can just think of it as a space of connected graphs whose fundamental group is the free group on n generators, MGN. So what I mean by a graph, well, graph I'm viewing as a metric space. So the edges have positive real lengths, and that gives you a path metric on the graph. And for simplicity, I want to normalize so that the sum of the edge lengths is equal to 1. So I don't want to distinguish between taking a graph and multiplying it, all the edge lengths by 2. It's the same graph to me. Since I'm thinking of graphs as metric spaces, if I have a vertex in the middle of an edge, it doesn't really change the metric space. So I'm going to not allow bivalent vertices. And for this space, MGN, I'm not going to have any univalent vertices either. So in order to have a graph with fundamental group Fn, well, I can't have a circle with fundamental group F1 without having a bivalent vertex. So, and no univalent vertices. So n is at least 2 for this space. So let's look at what happens at n equals 2. There's 3 kinds of graphs that fit my criteria. There's graphs with 1 vertex and 2 edges. And there's a graph with 2 vertices and 3 edges. There's 2 kinds of those 3 kinds of graphs. And I'm normalizing so that the edges have lengths a and b, and a plus b is equal to 1. Here I've got 3 edges, a, b, and c. A plus b plus c equals 1. And here again, a plus b plus c is equal to 1. So all I've said so far is a set of points, and so I need to make this into a topological space. So I say points in this space are close to each other if they're close as metric spaces. In other words, you put the Gromov-Hausdorff topology on them. So for instance, there's a whole set of graphs with a plus b equals 1 that forms a whole line. In the middle of the line, a and b have equal lengths. Towards the right and the left, well, you can't make b shrink all the way to 0 because that would change the fundamental group, and you also can't shrink a all the way to 0. Oops, that's a blue point. So it's an open interval, a plus b equals 1. So continuing this picture, if you have 3 edges, a plus b plus c is equal to 1 gives you a triangle. And if you let a shrink to 0, you go to the left-hand side of this triangle, and you get points on the blue line there that's not actually in the space. Same thing happens if you shrink c to 0, you go to this side of the triangle. Right. Oh, I wanted to say something actually about the last picture. Notice that this guy on the left, this guy with the a tiny, is actually isometric to that guy on the right with the b tiny. So those are the same metric space. So in fact, I don't get a whole line of points. I only get half of the line. It stops when a is equal to b. Right, stops here. And I really only get half of the line in my space. And similarly, in this picture, I have a whole, I also have a symmetry of this graph. And I only get half of the triangle in my space. Because the other half is just same graph, flipped. And in the picture with the 3 edges and 2 vertices, looks like that. There's actually lots of symmetries of the graph. I can permute A, B, and C, so I get I divide this into sections like that, and I get just one little piece. All the graphs are isometric to something in that little piece. And so the entire picture for n equals 2 looks like that. Yeah, just the yellow stuff. They're glued together because the bottom of this guy is the same as the top of this guy. So I want to say again that the blue points in this picture are not actually in MG2. Think of them as at infinity. And you can, if you like, add them, and you get something called MG2 bar. Okay, so that's the space. I wasn't allowing univalent vertices, but that's not really, I might as well. I can add univalent vertices if I want. Some people, physicists tend to call them legs. I tend to call them leaves. And so I have graphs. This is a graph with leaves. It's got 5 leaves. I've labeled them 1 to 5. And so that's in the space MG35. There's a slight subtlety to the normalization. I said I want the sum of the edge lengths to be equal to 1, but in fact, I only want the sum of the interior edge lengths to be equal to 1. I don't think of the leaves as having lengths, because in some applications, I want the leaves to be rays going out to infinity. Sometimes I want them to be points on the graph. I don't want the leaves to have lengths. If I did care about the leaf lengths, it would be easy to modify the space. I just have a product of leaf lengths. So it doesn't really change much about the geometry or topology of the space to have leaf lengths. Okay, so you notice I've labeled the leaves. So the symmetric group acts on the set of labels. So I can mod out by the action of the symmetric group, and I would get a space of graphs with leaves, but the leaves would be unlabeled. I would think of the leaves as unlabeled. So I've put a little U up there on top of the decorated MGNS with U to indicate that the leaves are unlabeled leaves. Okay, so those are some spaces of graphs. Of course, in this version, if I take S equal to 0, I just get no leaves. So that's MGN, the same one I talked about before. So let's think about what these spaces look like in some examples. If if the fundamental group is trivial, then I need at least S4 leaves to get an internal edge. And remember, I've normalized so that the sum of the internal edges have length 1. So that's supposed to be a 1. So there's exactly 3 different graphs that I can get with labeled leaves with 4 leaves. So the whole space of graphs is 3 points, those 3 points. I like to think of that as 3 points. Let's see. Whoops. 1, 2, 3. That's an S0 wedged with an S0. Okay? Of course, if I don't label the leaves, then those are all the same graph. So I only have 1 point. So whoops. I did that in the wrong order, didn't I? If I label the leaves, I get 3 points. If I don't, I get 1 point. And in general, we know everything we could possibly want to know about this space. It's always homotopy equivalent to a wedge of spheres. In fact, we know the spheres are S minus 4 dimensional, and there's always s minus 2 factorial of them. The symmetric group of order s on s minus 2 acts on this set of spheres, and it gives you a regular representation of sigma s minus 2. So we know this space, and we know, right, so if you look at the top homology of this space, it's s minus 2 factorial dimensional, and it's a regular representation of the symmetric group on s minus 2 letters. So that was easy. So we could move up to rank 1. So what happens in rank 1? Well, you need at least one leaf in order to get an admissible graph, because if you don't have any leaves, you have a circle and you can't put any vertices on it. So for, it doesn't matter whether you label the leaf or not. It's just one leaf. And so that gives you a single point. So that's s equals 1. If s equals 2, you've got two possibilities. You might have both leaves attached to the circle, or you might have a little one leaf attached to another leaf. So you get, you can think of this one leaf as the first leaf as pointing to a base point on the circle, and then the second leaf wraps around the circle, giving you a whole circle of graphs. On this one, the length of this line could change from 0 to 1, giving you a line of graphs. But just as in as before, this graph here is isometric to this graph. So in fact, you don't get the whole circle, you only get half of the circle. You only get, this half is what I've drawn. So this here is a picture of, this is a picture of the entire space MG12. So this little line coming off doesn't really do much for the topology of the space. You can just shrink it, and that's just homotopy equivalent to a half circle. The circle modulo A is equal to minus A, where, well, A was that length. A was this length. Right, and then the theorem for this is the theorem, the picture in general. If you have S leaves, well, you can assume that they're all attached to the circle. So S minus 1 of them go around the circle, giving you S minus 1 copies of the circle. And again, there's a flip that identifies a configuration up here with a configuration down here. So you get the entire MG1S is homotopy equivalent to S minus 1 dimensional torus modulo an involution, a flip. So if S minus 1 happens to be even, this is called a Kummer variety. Right. So we know everything we want to know about this space too. But it gets more interesting when the n in this, the rank of the fundamental group gets bigger. Right, it's more complicated. So I've now described all the spaces that I'm going to talk about today. And I just like to point out that these spaces, it turns out, are interesting to lots of different people. So evolutionary biologists like this space, especially the n equals 0, that's the trees space. They think of it as a space of phylogenetic trees. They like to study geodesics in that space and do statistics on that space. Algebraic geometers like this space, especially algebraic geometers of the tropical variety. They call it the space of tropical, the moduli space of tropical curves. they also especially like to add those blue points at infinity. They call that's like, when you take Teichmüller space and you mod out by the mapping class group, you get the moduli space of Riemann surfaces, but algebraic geometers don't like that. They like to compactify that instead. So the same picture here. Quantum field theorists like this space because, especially if you have leaves, because it parameterizes Feynman integrals for if you want to compute the n-loop contribution to the amplitude of some scattering process, you integrate something over this space. And topologists studying diffeomorphisms of higher dimensional manifolds like this space, turns out there's a certain Lie algebra attached to that comes up in various guises, including as a chain complex for this space. I mean, the chain complex for this Lie algebra comes up as a chain complex for this space. But this is supposed to be a geometric group theory, at least partly, conference. And so the question is, why would geometric group theorists be interested in this space? And basically goes back to 1986, where Mark Culler and I showed that the group of outer automorphisms acts on a certain contractible space called outer space with finite stabilizers, and the quotient by the action is the space of graphs, MGN. So there's a map from outer space to MGN. And what's the fiber over a graph? It's the set of isomorphisms of the graph with the fundamental group with Fn. So that's a discrete set. You thought of that. So it's like a covering space, but it's like an orbifold cover. But I don't know if you can call something an orbifold if there's no manifold in the picture. But anyway. And so the point about this is that the group of outer automorphisms of a free group acts by just changing the isomorphism. So if I have an automorphism of the free group, alpha, then I can compose that gamma of alpha and get a new isomorphism of the free group with the fundamental group, and that gives me a different point in my space. Right. And why did I say that out Fn acts instead of out of Fn? The point is that we haven't fixed a base point for this space. So when I talk about the fundamental group of this space, it's not actually well defined. It's only well defined up to a change of base point. Right. So it's pretty easy to see that the stabilizer of a point under this action is just the set of isomorphisms, of automorphisms of the free group that can be realized as isometries of X. For instance, if my point is just this rows on 3 generators, and I've identified the fundamental group of that by maybe sending X to that loop, Y to that loop, and Z to that loop. And if I look at the automorphism that changes X to X inverse, well, what does it do? I can realize that on this graph. It just flips the X loop. That gives me the same graph, the same point. Yeah. Same, yeah. So, yeah. So any automorphism of the graph is going to give me, is going to induce an automorphism of the free group that fixes the graph. And then this contractibility theorem, right, so we've got groups. We've got actions of groups on a space with quotient, the moduli space of graphs. And Hurewicz theorem implies that if you have a homotopy invariant of this space of graphs, that's actually an invariant of the group. That's just because of the fact that CVN is contractible and the action is proper. In particular, cohomology. You can compute cohomology of the group by computing cohomology of this space. So that's what we're going to be interested in today, is cohomology. So you may have seen descriptions of outer space before, where instead of talking about an isomorphism of the free group to the fundamental group of the graph, I talked about, or somebody talked about homotopy equivalences of between rows and the graph. So rows here is just a graph with one vertex and n loops, and I identify the fundamental group of the rows canonically with a free group by labeling the petals, by orienting the petals and labeling them with the generators of the free group. And this works because homotopy equivalences of the rows give you out of Fn, well, of course, two homotopy equivalences that are homotopy equivalent to each other give you the same isomorphism on the fundamental groups. So you have to talk about pi 0, which is, yeah, homotopy classes of homotopy equivalences of the rows. Okay. Anyway, that's out of Fn. And so then you think of CVN as pairs consisting of a graph and one of these maps, which is called a marking. And of course, this is only, the equivalence relation here is, well, isometries of X and homotopies of G. So this description in terms of markings G is convenient when you want to add leaves to your picture, to your graphs. So in that case, we fix, instead of a rose for our fundamental object here, we pick a rose with thorns or something, leaves, which we label bound delta 1 to delta S. I think of them as boundary points. And instead of marking a graph with leaves with, yeah, so I mark a graph with leaves with a homotopy equivalence from this guy to my X, but I have to send the leaves to the leaves. So if I have a point, a graph with leaves labeled 1, 2, 3, my homotopy equivalence has to send boundary 1 to 1, boundary 2 to 2, and boundary 3 to 3. And of course, again, there's an equivalence relation on these pairs consisting of a graph with leaves and a homotopy equivalence. But I have to assume that all of my homotopies always preserve the labeled leaves. Okay? And Alan Hatcher proved, in fact, that if you add leaves, the space of graphs with leaves of pairs consisting of xg is still contractible. So if you just have one leaf, what you can do is you can think of that leaf as pointing to a base point on the graph. Okay, and so then we're talking about homotopy equivalences of this graph that preserve a base point. In which case, we're talking about the group of automorphisms of the free group instead of outer automorphisms of the free group. We do have a base point that we've chosen. But for S bigger than 1, there's actually two interesting groups here. So we can look at homotopy equivalences of this thorned rows that preserve the boundary points, but possibly might mix them up. So all maps and homotopies have to preserve the boundary, but you're allowed to permute the leaves. So we'll call that BNS. And then there's a pure version where you insist that all homotopies actually fix the leaves. They send the ith leaf to the boundary I to, They can't permute the leaves. They have to actually fix them. So there's an analogy that should jump out at you here. And why did I call it BNS? This is like the braid group and the pure braid group, right? Both of these guys act on the space of graphs with leaves. And if you take the quotient by A and S, you get this moduli space of graphs with labeled leaves. And if you take the quotient by B and S, you get the moduli space of graphs with unlabeled leaves. So I said I was interested in invariance of the group that I can compute using these spaces. In particular, I'm very interested in rational cohomology. So let's look at MGNS. So that's the same thing as the rational cohomology of A and S. I'll omit to write coefficients from now on. All coefficients, well, for a while in this talk, are trivial rational coefficients. So we know the MG0S is homotopy equivalent to a wedge of spheres of dimension S minus 4. So I'll let you compute the cohomology of that space. You can probably do it. MG1S, you might have slightly more trouble, but not too much, especially if you know about cohomology. So the cohomology of a torus is just the exterior algebra on the field of dimension, the vector space of dimension S minus 1. But if you mod out by this relation, all you get is the even part of the exterior algebra. So that also is pretty easy to compute. Maybe yeah. But for n equals 2, it's more interesting. And a good tool to use to understand the cohomology with of A and S is the so-called Berman exact sequence. This is called the Berman exact sequence by analogy with the Berman exact sequence in mapping class groups, where you have the mapping class group of a punctured surface, and you forget the punctures. You just think of that as a mapping class group, a mapping class of the surface, and then in the kernel, you're allowing the punctures to wander around the space, so you get S copies of the fundamental group of the surface. Or in this case, we're talking about points wandering around on the graph instead of the surface, so you get S copies of the fundamental group of the surface. So whenever you have, let me go back to this short exact sequence. Whenever you have a short exact sequence, if you're interested in cohomology of groups, you have to learn about spectral sequences. There's something called the Hochschild-Array spectral sequence that computes associated to any short exact sequence of groups. And if you look at that spectral sequence, you can understand the entries on the E2 page in terms of the representation theory of out of F2. And out of F2 turns out to be actually isomorphic to GL2Z. And people know a whole lot about the representation theory of GL2Z. And in fact, using that spectral sequence, you can compute the cohomology of MG2S as a sigma S module, symmetric group module over the number of punctures. And the answer turns out, not surprisingly, because you're talking about GL2Z, in terms of modular forms. So you're getting some very interesting cohomology classes appearing that correspond to modular forms. Right, but anyway, that's been completely calculated by Conant, Hatcher, Kasabov, and myself in 2017. Okay, so that takes care of n equals 2. All right. And that was for MG2S. Remember, that computes the cohomology of A2S. But what about B2S, the braid group version, as opposed to the pure braid group version? Well, there's also a short exact sequence, of course, from the BNS to the symmetric group, and the kernel is the pure version, ANS, just like for pure braid groups and braid groups. And so remember, we're only talking about rational cohomology here, so actually the cohomology of BNS is just the sigma s invariance of the cohomology of ANS. So that's also easy to see with the spectral sequence because finite groups have no rational cohomology. So if you know about spectral sequences, there's only one column, and this is it's a spectral sequence that converges the cohomology of this. There's only one column, and that's the cohomology of this. So that's, if you know about spectral sequences, that's a very easy computation. And you can do this. Remember, up here we computed this thing as a sigma s module. So we know, we found the irreducible decomposition of this guy as a sigma s module. So we can just look for the trivial modules, and you get, if n equals 2 and s is bigger than 2, get the cohomology of B2s is q in dimensions 0 and 1, and 0 bigger. So if you are familiar with braid groups, you'll know that this is also the cohomology of the braid group. And notice that it's independent of s, as long as s is at least 2. I guess B1 doesn't make sense. Okay. Yeah. So for n equals to n bigger than 2, it gets much harder to compute anything. And so instead, you can try, it's kind of standard in cohomology theory. If you can't compute cohomology, try to at least compute the Euler characteristic. So the Euler characteristic of the moduli space of graphs with no leaves is the alternating sum of the dimensions of the homology of out of Fn. And if you got leaves, it's minus the sum of minus 1 to the I times the dimension of hi of an sq. So it turns out that the alternating sum of the homologies is not so easy to compute either. However, there's a variant for groups. I mean, we're talking about the Euler characteristic of spaces, but we've identified those with Euler characteristics of certain groups. Well, we've identified these spaces with certain groups. And for groups, there's a variant called the rational Euler characteristic. Unfortunately, it's called chi of g, which is not nice because it's not the alternating sum of the dimensions of the rational homologies. It's denoted chi of g. So if it's not the alternating sum of the dimensions of the homologies, what is it? Well, turns out if you have a group and it acts properly on a contractible space, and if it's got a torsion-free subgroup of finite index, then if you take the torsion-free subgroup of finite index, actually has an Euler characteristic. This is the same as the Euler characteristic that you know and love. And if you take that Euler characteristic and divide by the index of the group, you actually get an invariant of G. So the point is, if H doesn't have any torsion, and G acts properly on X, so H actually acts freely on X. Stabilizers are trivial. So the quotient of a contractible space by a free action, well, that's a covering space. And that gives you the universal cover, and the Euler characteristic of H is, and the cohomology of H is just the cohomology of that space on the nose with any coefficients. And so you can actually compute the Euler characteristic of the group from the Euler characteristic of the space. Yeah. So this other version, this rational Euler characteristic, has a property that's missing for the alternating sum of the Betti numbers. Namely, if you have a short exact sequence of groups, and all of the groups have Euler characteristics, have rational Euler characteristics, then the Euler characteristic of the guy in the middle is the product of the Euler characteristic of that one and the Euler characteristic of that one. So that's a very useful property. For instance, we have this exact sequence that I mentioned before, the Berman exact sequence that relates these groups A and S to out of Fn. So if I want to compute the Euler characteristic, the rational Euler characteristic of A and S, all I have to do is compute the Euler characteristics of that and that. That one's easy, and that one's not so easy. But the point is I can reduce the whole problem to just studying the Euler characteristic of this. So that's what I'm going to do. I'm just going to tell you what we know about that. Yeah?
So is this rational Euler characteristic, can one interpret as some kind of orbital
It is.
characteristic for the space? Like keep
Yeah.
track of the local.
Yes, exactly. That's what it does. Okay, so how do you compute the, I think this is maybe an answer to Yair's question. How do you compute the rational Euler characteristic of a group? You got an action on a contractible CW complex, which is proper and co-compact. Then the Euler characteristic of G can be computed as the sum over orbits. I guess I can point with my technology instead of my finger. This means, whoops, that. That means orbits of cells. You take -1 to the dimension of the cell, as you would expect, but you have to divide by the order of the stabilizer of the cell. So unfortunately, the action of out of Fn on outer space is not co-compact, but there is a co-compact spine. So points in outer space are pairs consisting of a graph and a marking, but this spine happens to be a cube complex. And there's one k cube for each triple, where x, so I've added phi to my notation. Here x is a graph, an admissible graph, g is a marking, and phi is a forest with k edges. So let me show you how that works for n equals 2. This is a picture of all of outer space. The little symbols on the edges tell you what the isomorphism is that defines the point in the middle of each simplex. So I've left off the barbell graphs, but basically that's the space, and the spine that's why it looks kind of like a spine skeleton. Anyway, that's the spine, and I claim that's a cube complex. So what's a cube? Here's a cube. It corresponds to this graph, but I've shrunk this forest to get this graph. So I start with this graph, I shrink a forest, I get that graph, and I get a little cube, a one-dimensional cube. If I shrunk 2 edges, I would get a 2-dimensional cube. If I shrunk 3 edges, I would get a 3-dimensional cube. So this spine is always a cube complex, and Brown's formula translates to, if I want to compute the Euler characteristic of out of Fn, I have to add, instead of over isomorphism classes of graphs, I have to add over isomorphism classes of pairs consisting of a graph and a forest. I have to take -1 to the e of phi, because that's the dimension of my cube, divided by the group of automorphisms of x that take the forest to itself. So I can simplify this formula a little bit using the orbit stabilizer theorem. the set of automorphisms of the graph acts on the set of forests in the graph. And the orbit stabilizer theorem can simplify this formula to make it the sum over isomorphism classes of graphs of a number tau of x divided by the group of automorphisms of x, where tau of x is the sum over all forests in the graph of -1 to the e of phi. So this is simpler because instead of adding over isomorphism classes of pairs, I'm now adding over isomorphism classes of graphs. So yeah, I think it looks easier. Anyway, this was calculated for n less than or equal to 11 by John Smiley and myself in 1987. And we sent the results to Don Zagier and asked him what these numbers were. And he said he didn't know, but he calculated them for n up to 100. They were all negative. They all seemed to be growing very, very fast, but we couldn't prove anything about that. We couldn't prove either of those statements until I met a physicist, Michael Berinsky. In 2020, we used some graph counting methods that he was using to count Feynman diagrams to prove that the Euler characteristic is always negative, and that's what it's asymptotic to n over e to the n times 1 over n log n squared. Okay, so what time is it? 42. Well, let me tell you epsilon about this. You can tune out if you don't. Yeah. So here's the idea of the proof. No details whatsoever. That's the Euler characteristic. It has to do with counting graphs, counting forests in graphs, and counting automorphisms of graphs. So there's a cute combinatorial lemma which you can use to prove that the sum of this number tau of x times -1 to the if you take all subgraphs of x and add up tau of gamma times -1 to the number of edges in gamma, you get 0. So you put this into a stupid equation in the ring of formal power series. Namely, 1 is equal to the sum over all x of the sum of all these numbers times z to the e of g minus v of g. Why is this a stupid equation? Because this number is 0 unless x happens to be the empty graph, in which case it's 1. Okay, so that's a pretty easy equation in the ring of formal power series. But it turns out, this doesn't look so far from that. And it turns out if you manipulate it and you eventually get an asymptotic expansion for this function in this scale. This is the gamma function. And the coefficients of this asymptotic expansion are the Euler characteristics. So as I said, this is a very quick. So what does this mean in asymptotic expansion? It means that if I take this function and I add and I subtract off the first n minus 1 terms, I get something that's O of phi of n as n goes to infinity. So what? So we have an asymptotic expansion for this function. So what Berinsky did is he knew an asymptotic expansion for something called the Lambert W function. And given an asymptotic expansion for something, you can manipulate it into an expansion using any scale. He put it in the scale phi k, where phi k was his gamma functions. And he got a new asymptotic expansion for the same function in the same scale. So asymptotic expansions of the same function in the same scale have to have the same coefficients. That's a basic feature of asymptotic expansions. So then you can use known results about the Lambert W function to deduce results about the coefficients, which are the Euler characteristics. Okay, so this is all. You can read about this. It's in commentary. All right, so that was the rational Euler characteristic. But what about the actual Euler characteristic? I claimed I was interested in space for lots of different reasons. It turns out that if you know the rational Euler characteristic, it doesn't necessarily tell you anything about the real, about the alternating sum of the Betti numbers. For instance, the rational Euler characteristic of GLNZ is always 0. But GLNZ has lots of very interesting cohomology. So we really want to know about this number, which I'll call E of ANS to distinguish it from chi of ANS. So this is a conference on randomness and other things. So let me just say that so the difference has to do with automorphisms of graphs, right? Between the rational and Euler characteristic and the actual Euler characteristic. So there's a theorem that says random graphs don't have any automorphisms. Now, what does this mean? What does random mean, et cetera? How do you quantify random? But Kontsevich conjectured that the rational Euler characteristic should be asymptotically the same as the alternating sum of the Betti numbers, as E. So people have tried to calculate this Euler characteristic. The most impressive result was due to Morita, Sakasai, and Suzuki, who calculated for, in rank 11, the Euler characteristic is minus 1202. So it looks like it's at least starting to grow pretty fast. Like we know the rational Euler characteristic grows fast. And then in 2023, this year came out, Berinsky and I proved that the Euler characteristic of MGN is actually, well, it's almost exactly the same. This part here, that was the growth rate of the rational Euler characteristic. And, but there's this e to the minus 1/4 out in front. So we disproved a conjecture of Kontsevich. Yeah. But he was close. Right. So the way we proved that was by first deriving a new generating function for this Euler characteristic. By using different ways of counting graphs, which I probably won't get to. But this new generating function gives a very effective and efficient way to compute this number, E of out of Fn. And Berinsky used a computer program by, that's not the right name. And I can't remember the right name at the moment. Lay? I don't think so. This is his first name is Jos, but it's, yeah, I'm sorry. No, that's somebody else. This is a physicist. I'm sorry. This is very bad. Anyway, this guy is a physicist, and he invented a computer language for doing large calculations. And he and Michi implemented this algorithm and spat out the results of the computations in ranks up to 100. And we were very happy that the results actually agreed with Morita, Sakasai, and Suzuki's results. So it seems that our theorem might be right. Right. So Berinsky and his friend wrote this up, and they wanted to write it up as a separate paper concentrating on the implementation of this algorithm in this computing language. But Michi said, well, we should do something else, so let's compute the Euler characteristics of Mg and S for NES. So a variant of what we did for MGN works, in fact, for any number of leaves. And in fact, you can also compute, you can either do it for labeled leaves or unlabeled leaves. So after they did this, there was this really weird phenomenon that appeared. So when they computed this one, so this one grows really, really, really fast, as you might expect. This one grows really fast for a while until it gets to S equals n. And then all of a sudden it stops changing. The Euler characteristic stops changing. Not only that, but it drops dramatically. So, here it's, for n equals 10 or something, by the time you get to 10, there's tens of thousands of cohomology classes, and then all of a sudden there's 300. So that seemed very bizarre. But then you remember what happened with the braid group and the pure braid group. So the cohomology of the braid group does not stabilize, of the pure braid group does not stabilize. It satisfies something called representation stability, if you know about that. These groups also satisfy representation stability, these guys. But the braid group, it doesn't depend on S. And it turns out that, so that was the conjecture that that not only the Euler characteristic, but in fact the entire cohomology is independent of S, if S is bigger than the genus of the graph, the rank of the graph. And they proved it. So this is a new theorem of Borinsky, and this is not his name, I'm sorry. I was writing late last night, and I didn't think of it. So I know somebody else with a similar name. The cohomology, the cohomology is in fact independent of S, and again, the proof is by looking at this Hochschild-Sayre spectral sequence we looked at before, for when we calculated H, the cohomology of B of A to S. And so what you do is you look at the E2 page, you use the representation theory of JL and Z and Schur-Weil duality to prove the fact that the invariant, the symmetric group invariant terms on the E2 page don't depend on S for S bigger than n. And since they don't depend on S on the E2 page, they don't depend on S when you go to infinity either. So in fact, yeah, it's true. The cohomology of these, the BNSs are independent of S if S is big enough. Right. Okay, but this obviously leaves some questions open. So the first question comes just from the computation of, for S equals 0, no leaves. So that gives you the E of out of Fn. And it shows it's got huge, huge amounts of odd-dimensional rational cohomology. But it's also known that as n increases, the homology stabilizes. The ith homology stabilizes. So if n is much bigger than I, there isn't, in fact, any cohomology at all. This is a theorem of Soren Galatius. Okay, so there's no cohomology in large dimensions. And in fact, only one odd dimensional class has ever been found in the cohomology of out of Fn. And that's in H11 of out of F7. And that was done by by a huge computer calculation by Laurent Bartholdi in 2017, using a huge amount of computer time and a lot of clever ideas to reduce the calculation to something manageable. In rank 11, there's a lot of graphs, even if you don't have leaves. So, yeah. Calculating homology by looking at kernels and co-kernels of matrices gets pretty hairy. Right, so the elephant in the room here is, where's all this cohomology coming from? You know? And then this new computation, so we have the fact that this is non-zero, but it's very small. It drops dramatically after n gets past s. And so that's also a question that I would really like to understand. So all of this is in the stuff about out of Fn, E of out of Fn has just appeared in Advances. And for some reason, Quanta magazine got interested. So you can also read about it in Quanta magazine. This stuff is on the archive. I haven't really told you how you make any of these generating functions, and that's a nice story in itself. I haven't told you how you compute the asymptotics of these generating functions. That's a nice story in itself, but each of those I think is a separate lecture.
Questions? I have a quick question. Like, what's the story in mapping class groups? Do we know the Euler characteristic there, or?
Yes, the Euler character. So this is a famous theorem of Herrer and Zagier for closed surfaces. That the Euler characteristic is basically the zeta function, zeta of s of n, and so this stabilization phenomenon, it doesn't occur in mapping class groups. And there are also several other complexes, graph complexes defined by Kontsevich that are related to mapping class groups and out of Fn and other things. There's the associative graph complex is related to mapping class groups. And so this phenomenon doesn't happen for that one. But it also doesn't happen in the commutative graph complex. It seems to be something specific to the Lie graph complex and the braid group. So, yeah.
Rational Euler characteristic and the alternating sum.
It's the same.
They're the same in the mapping class group case. Okay.
Yeah. I mean, so you can compute the Euler characteristic of a space by looking at its rational cohomology just as well as looking at its integral cohomology. Is that the question? Yeah.
Find two different notions, right? One was, you were calling one thing E and the other
yes.
thing chi.
Oh, yeah.
I was asking if they were the
yeah,
same.
no, this was about, sorry, the rational cohomology, the rational Euler characteristic of the mapping class group is the zeta function. The regular Euler characteristic is more complicated, but they also figured that out. Yeah. Sorry, I misunderstood.
Any other question? Okay. Let's thank Karen again.